All right, welcome to The Explainer. Today, we are diving headfirst into one of the deepest, most mind-bending mysteries in all of science, the quantum measurement problem. It's a question that really challenges our basic understanding of reality and suggests that the universe might actually change its behavior just because we're looking at it.
So let's kick things off with an idea that kind of flips this whole mystery on its head. For centuries, we just assumed everything had to be one thing or another. But what if the problem isn't with reality, but with the words we're using? This quote gets right to the heart of it. The key isn't that light is both a particle and a wave, but that it's really neither.
To really get what that means, we've got to go back to the paradox that started this whole mess, a baffling contradiction that even the smartest people in physics had a hard time accepting.
You know, back in the day, in the world of classical physics, everything was, well, it was simple. Things were sorted into neat little boxes. You had particles, like a tiny little ball, a specific object in a single spot. And then you had waves, these spread out things, like ripples in a pond. They were totally different. Nothing could be both.
But then, boom, the double-slit experiment comes along and just shatters that whole picture. So physicists shoot single electrons one by one at a wall with two slits in it. When no one's watching, the electrons make this interference pattern on the screen behind them, a pattern that could only happen if each electron was acting like a wave going through both slits at the same time. I mean, how crazy is that? But then, and this is the kicker, the moment they put a detector there to see which slit it went through, poof, the wave pattern disappears. Suddenly they're acting like little particles again. The act of measuring literally forced reality to pick a side.
And this right here, this is where things get really weird. This isn't just some cool lab trick. It points us straight to the heart of the mystery we're looking at today, the measurement problem. So what in the world is going on here? Well, quantum theory says that before we measure something, it doesn't have a definite state at all. It exists in what's called a superposition, kind of like a ghostly cloud of all its possibilities at once. That electron wasn't going through the left slit or the right slit. It was in a state of going through both at the same time. And this idea, well, it leads to some pretty mind-bending, almost absurd conclusions when you try to apply it to our world. You've probably heard of Schrödinger's cat. It's a thought experiment where a cat's life is tied to a random quantum event inside a box. According to the math, until you open that box and look, that cat is in a superposition of being both alive and dead at the exact same time.
So this all forces us to ask this huge, almost philosophical question. Is reality not even fixed until we observe it? I mean, why would the universe seem to care whether we're paying attention or not?
Well, to even try and answer that, physicists have come up with some seriously wild explanations. Let's call them interpretations. We're going to look at the three main suspects for what's really happening under the hood. First up, we've got the classic, the most established explanation, the Copenhagen interpretation. It basically says, yep, observation is special. The act of looking forces that ghostly cloud of possibilities, the superposition, to collapse into just one single concrete reality. In this view, we, the observers, play a part in creating the outcome. Now, why is this one so popular? Well, it's pretty simple, actually. It just works. It's a practical, no-nonsense approach. The predictions it makes, they match up perfectly with what we see in experiments time and time again. It doesn't really explain why it happens, it just tells us how to do the math. And the math is incredibly accurate. Okay, so our second suspect, it takes a completely different road. The many worlds interpretation just gets rid of the whole collapse idea altogether. Instead, it says, get this, every single possibility actually happens. When that electron hits the slits, the universe splits in two. In one universe, it goes left. In another, it goes right. The cat is alive in one universe, and, well, you get the idea. So yeah, it's mathematically clean, but it comes with a seriously heavy price tag. It's asking us to believe in an almost infinite number of parallel universes that we can never, ever test or see. And that's why, as you see here, a lot of physicists call it metaphysically extravagant, which is a nice way of saying it's just too much.
And that brings us to our final suspect, which really tries to bring back some good old-fashioned order and predictability. The pilot wave theory says, hold on, there's no randomness here. It claims the particle always has a real location, but it's being guided on its path by a hidden pilot wave that we can't see. So the wave goes through both slits, but it steers the particle through only one of them.
But here's the catch. This so-called pilot wave and all its hidden variables are totally unobservable.
So critics basically say it's adding all this extra complicated stuff just to avoid how weird quantum mechanics is, but it doesn't actually give us any new predictions we can test.
All right, so we've got three totally different pictures of what reality could be. Let's put them side by side and see how they really stack up.
This chart really lays out the trade-offs, doesn't it? You've got Copenhagen, which works, but makes reality kind of observer-dependent. Weird. Then you've got many worlds, which is mathematically clean, but, infinite untestable universes. And finally, Pilot Wave gives you that certainty back, but it does it with these hidden things we can never find. There's just no easy answer here. It's like you have to pick your favorite flavor of weird.
But this brings us right back to where we started. What if this whole debate, this whole search for the right interpretation, what if it's all based on a big misunderstanding?
So some physicists are now saying that trying to cram a quantum object into one of two boxes, wave or particle, that's the real problem. As this quote puts it, we might be dealing with something way more complex, something our everyday intuition just can't handle. I love this analogy because it makes the point perfectly. Right? If you're walking to your neighbor's house, it's totally fine to think of the Earth as flat. It's a useful model. But if you're flying across the ocean, you'd better treat it like a sphere. The model changes depending on what you're doing, but the Earth itself, it isn't just flat or just a sphere. It's this incredibly complex thing. And maybe, just maybe, it's the same thing with light and electrons.
And to try and get a handle on this richer reality, people have even started suggesting new words. One idea is a fieldifical, a name that tries to mash together the field of a wave and the particle part into one single concept. It's basically an admission that our old vocabulary just isn't cutting it anymore.
And that leaves us here, not with a neat and tidy answer, but with a question that's even deeper than the one we started with. If our most basic ways of describing the world, wave and particle, are just rough approximations, then what does reality actually look like at the bottom? It's a mystery that is still pushing science to its absolute limits, and it's just fascinating to think about.